All right, so the plan for today is just another reminder that there's a supplement for the graphing tool for chapter 4 on WebAssign on Blackboard. So you can check out Blackboard under the supplemental materials folder and take a look through that supplement. I got some questions over the weekend where I think people were just maybe they understood the material, the math side of things, but we're struggling with that graphing tool. So just a reminder that that supplement is there with a little more information. And then of course, um, last class meeting, we talked about it a little bit too. Um, the plan for today is to finish 4-3 graphs with intercepts, super quick little, one little detail to finish up there. And then most of today, we're going to spend doing a Unit 1 exam review. As part of the review, we'll also take a look at a couple of problems on WebAssign, where we'll go through some of those, where we'll go through graphing some problems with some, with using that tool. So that'll hopefully just be a review for how to use that tool and so on. Note that the Unit 1 exam is this week. So on the course schedule, it's kind of like, slated on there as on Thursday, but it's, I gave you a full week. So it's due next Tuesday, or this coming Tuesday, however you want to say it, the 12th at 11:59 p.m. Normally things would be due Sunday, but I figured since we didn't have class until today, I wanted to give you those extra couple of days next week. So, typically it would be something like Monday to Sunday. That would be in line with kind of how our homework and all that works. But I think having it due on Tuesday, number one, gives you a couple of extra days. And number two, puts the due date not on a Sunday. So that way, if something goes wrong, it's maybe a little easier to troubleshoot. And extremely important, don't wait until the last minute or the last day to complete the exam. If you wait until, I don't know, 9 p.m. or something on Tuesday, your options are going to be pretty limited, right? Reaching out to me, like I'm probably not going to be checking my email at that point. You're going to have fewer options, like say your internet goes out and can you go to the library instead, or can you go to a friend's house or something and take it there? So I strongly recommend giving yourself at least a full day, preferably more, buffer until the end of the exam window. So I would say plan to take it Monday at the latest, maybe over the weekend, or maybe even later this week. And, that extra one day of studying probably isn't going to be super helpful relative to the amount of risk that brings into the equation. If you wait until, Tuesday evening or something like that to take it. Despite me saying this every semester in every section, people always do that. And some people have been burned in the past. So some people have went right up to that deadline, something happens, they can't take the exam. And as it says in the syllabus and in the announcement and so on, the Blackboard announcement that I posted last night, there are no due date extensions on this exam because it's open for a full week window. That should give you plenty of flexibility to be able to take the exam. So there shouldn't be a reason for a due date extension. It would have to be something quite extenuating to warrant an extension. And the quote of the day, now that we're kind of approaching midterm exam time and, just the middle of the term when a lot of things like course projects and papers and so on are due, is from financial guru, if you want to call him that, Dave Ramsey. Don't agree with 100% of what he says, but a lot of what he says is good advice for his audience. And one of his quotes is, "Desperation precedes stupidity." We tend to make decisions that aren't as high quality as kind of our average decision making when we're desperate. So when we can, if we can, we should avoid putting ourselves in that position. If you know that you have an exam coming up, that's due a week from now, give yourself a little bit of buffer, give yourself a day or two margin in case something goes wrong. If you have a term paper, say in your English class or something that's coming up in 2 weeks, that's due in say 2 weeks or whatever, right before spring break, Don't wait until the night before and then get tempted to, do something with ChatGPT or something like that, that you maybe otherwise, that would be a decision you might not otherwise make. Okay, so before we move into section 4.3, are there any questions on anything so far?
Like, can you do like half of the let's say, can you do half of the exam like on probably like Sunday and half on like Tuesday? Is that possible?
No, you do have to take the exam in one sitting all at once. It's a 2 hour exam. So I think 2 hours is um a pretty lenient window. I don't think the exam will actually take you 2 hours, but that way, time shouldn't be that much of a factor. So I would schedule 2 hours for it. But and that's one other thing I forgot to mention is that there is a sample unit one exam posted that's very similar length, very similar problem choices, very similar types and difficulty of problems. So that you can also use that to judge um, your readiness for the exam or how long the exam will take. But you do have to take it in one sitting, and there is only one. You can only take the exam one time, and each problem is only able to be submitted one time. So unlike the homework where you have multiple problem submissions, for the exam you do only have one submission. However, after the due date for the exam, so after Tuesday the 12th, probably shortly after, maybe that Wednesday, Thursday, Friday, I'll go in and manually review every problem that WebAssign marked wrong on every student's exam. So I go through everybody's exam and I look at what you entered for every problem it marked wrong. And sometimes it's just, and I mentioned this in the announcement as well, but sometimes it's just a little syntax issue and I can manually give you full credit for that problem. Or sometimes it's kind of clear what the error was and it was a minor error and you get partial credit for that. So there's not a ton of partial credit. I do adjust for there being less partial credit in an online class by adjusting the difficulty of the problems that I choose relative to what I might choose for a paper and pencil campus class where you get a little more partial credit. So the problems on the WebAssign exam tend to be on average a little bit easier than a paper and pencil exam to compensate for the lower amount of partial credit. Yeah, Kiana has a question.
I was just wondering, I saw that the practice exams out of like 100 points, is any of that graded or no?
Do you mean the sample exam or the examity practice exam?
The actual, the sample exam.
Yeah, so the sample exam, I mean, WebAssign will grade it, but it doesn't count towards your final course grade.
Oh, okay.
Yeah. It might I'll have to double check. Sometimes I have the grade book settings a little bit wonky or something, but it shouldn't be counting towards your course grade in WebAssign or for the course. Yeah. Yeah. So the unit one practice, or sorry, the unit one sample exam is uh kind of meant to mirror the actual exam, and it's to really assess your readiness. It's not so much for a grade. So don't worry about what grade you get on it. It won't count towards your final course grade. The examity practice exam that's been up for a couple of weeks now is meant to practice the examity process, getting logged into examity, getting all of that set up, making sure that all the tech is working and all of that. That also does not count toward your final course grade. But that examity practice exam only has a couple of questions and it just is kind of dummy questions just to put something in there. And that also doesn't count towards your final course grade. But for both of those, I do very strongly recommend that you do both of those before you take before you take the unit one exam, the actual exam, just to make sure that the examity process is set up and you're familiar with it and that you know what's going to be on the exam. Yeah, Awan has a question.
Yeah, like on like my 4.2 homework,
Mhm.
like I didn't know how to like graph the points. Like I think I sent you an email about it. Is there like way for you to like unlock that homework again or no?
Yeah. If you sent me an email, if you emailed me yesterday, I'm gonna get back to my yesterday emails in today's office hours, so I should see that
Uh,
after today's class. And yeah, that's no problem to get a due date extension. And we will
okay.
review that as part of the exam. one review today, we'll take a look at going through some of how that graphing tool works. And then there's also the supplement posted on Blackboard that might also help.
Okay, thank you.
Yep, sure. Any other questions? Okay. So just a couple of quick problems on, just to wrap up section 4.3, graphs with intercepts. We talked last time quite a bit about intersections of, let me just come over here and for a quick review. We talked last time quite a bit about intersections of lines, graphs of linear equations with axes. So if these are the X and Y axes, we might have a point like this one here where maybe X is some number like 3 and Y is a number 0. That would put this on the X-axis because Y, the vertical distance, is 0. That means the point is on the X-axis. And vice versa, we might have, say, a Y value of 4 when X is 0, when we're on the Y-axis. When our horizontal distance is 0, we're going to be on the Y-axis. And we said that it can often be the case that these points are easy to find because one of our inputs, X or Y, is 0. That might make finding the other one a little bit easier. And if they're kind of nice points, like whole number points like this, being able to locate them on the axis, on the X or Y axis, might be a little bit easier as well. So if I gave you an equation of a line and said find 3 points, probably the first candidates that I would try is when X equals 0, what's Y? When Y equals 0, what's X? And then maybe look for a third point. Now, of course, we did talk about, we could have gotten, say, 0, 4/3 or something as one of, say, the Y-intercept. And that might not be a point that we'd want to graph. It might be kind of annoying to try to find that to make the point sit there on the WebAssign graphing tool or something. Or if it was like 17/3, that might be kind of annoying to figure out, okay, what 2 integers of 17/3 in between so that I can, put that point in the right place on my graph that I'm doing by hand. So, we might not always choose to use the X and Y intercepts as our 2 points that we're going to use to graph the line, but sometimes they can be helpful, and quite often it's important to know these intersections with these axes, these intercepts. So we have 3 questions here just to find the intercepts. And this is really more of a syntax question at this point than an actual calculation question. We've done this a few times already. But we notice that the X intercept, well, this is the intersection of the line with the X-axis. And specifically, it's the point of intersection. Didn't quite leave myself enough room, but this is the point of intersection of the line with the X-axis. So when the line intersects the X-axis, that's always going to be associated with Y being equal to 0, with the vertical height or the deviation vertically being 0. And it's going to be something like, say, A comma 0, where A is going to be some number, some X value. So our X-intercept is A comma 0, and that's provided that it exists, right? We could have, say, a horizontal line like Y equals 3, and this has no X-intercept. But if we have any line that other than a horizontal line, we'll have an x-intercept. And similarly, the y-intercept is the intersection of the line with the y-axis, that point. And that's always going to be when our horizontal deviation is 0, when x is 0, and y is whatever number b. So a couple of points here. One is that a vertical line, say like x equals -2, has no y-intercept, but it has an x-intercept. A horizontal line has no x-intercept, but it has a y-intercept. Every line will have at least one intercept. Most lines, in some sense, will have two intercepts. And the second note is that the intercepts are points. They're ordered pairs. And this is a bit of a semantics issue. You know, do we say that the up here, do we say that the x-intercept is 3? Well, no, we don't. We say the x-intercept is the ordered pair 3, 0. Do we say the y-intercept is 4? No, we say the y-intercept is the ordered pair 0, 0, 4/3. I changed that one, but so the intercepts are ordered pairs. Again, this is a bit of a semantics issue. It's a bit of just how we choose to define these things, but we do represent them as ordered pairs. Okay, so looking at this particular linear equation, 3x minus 5y equals -15. If I want to find the x-intercept, I need to plug in y equals 0, solve for x. If I plug in y equals 0, I get 3x minus 5 times 0, that term goes away, equals -15. And I see x equals -5. And here's where I might be tempted to just kind of, you know, if I was on WebAssign and it said, what's the x-intercept? I might just plug in -5. But remember, the x-intercept is a point, -5, 0. So we just have to be a little careful with that syntax. What's our y-intercept? That's when x equals 0, when our horizontal deviation away from the origin is 0. That's when we're directly on that vertical axis. If I plug in x equals 0, that 3x term goes away, and I get -5y equals -15, or y equals 3. And again, I need to make an ordered pair out of this. So 0, 3 is my y-intercept. So I don't think anything too surprising here as far as the math goes, just a little definition that we need to remember. So what if we had a slightly messier looking linear equation? -1/3 x plus 3/2 y equals 3/4. Let's find the x and y intercepts. The x-intercept, the intersection with the horizontal axis, is when the vertical component is 0, when y is 0. This tells me that -1/3 x plus 3/2 y, but that term is just 0 here, equals 3/4. And if I multiply both sides by -3, I get x equals -9/4. And again, I just have to remember to put it in the correct form. -9/4, 0. Similarly, my y-intercept. My y-intercept is the intersection of the line with the y-axis. that's when the horizontal component is 0, when x equals 0. That means this negative 1/3 x term, that term becomes 0. And I'm left with 3/2 y equals 3/4. And I might be able to guess the answer for y here if you're good at fractions, or we can multiply both sides by 2/3. I see my 3's divide out, and I see my 2/4. I can divide a factor of 2 out of top and bottom, and I get y equals 1/2. So my y-intercept, the ordered pair is 0, 1/2. And then for a last example, find the x and y-intercepts of the equation y equals 5x. So let's do the same thing. What's the x-intercept? The x-intercept is the intersection of the line with the x-axis, with the horizontal axis. That's when the vertical component is 0. When y equals 0, that says 0 equals 5x. But that says that x equals 0. My x-intercept is 0, 0. But we also kind of see that our y-intercept is 0, 0 as well, right? If we didn't see that, we could go here and say, well, what's the y-intercept? That's when x is 0. When x is 0, 5 times x is 0. So then y has to be 0. In this case, our x-intercept and y-intercept happen to be the same point. Why is that? It's because our graph of the line looks like this. The line happens to cross, say, the x-axis right at the origin, right where the y-axis also crosses the x-axis. So therefore, it crosses the y-axis at that same point as well. So we have kind of three scenarios. The kind of typical scenario is we get something like this, where we have two distinct intercepts, one x-intercept, one y-intercept. That's kind of the typical scenario. And we have a couple of special cases. We have, say, a horizontal line with one intercept, with a y-intercept. We have a vertical line with just an x-intercept, or we have a line that passes through the origin. These all look like y equals kx, with a single intercept at 0, 0. These vertical lines look like x equals a, and the horizontal lines look like y equals b. So this is the typical scenario, but we also have these few special cases down here that can pop up. And if I was just following my nose, I see that with y equals 5x, something like that, I do just find the same intercept twice. It's not really a big deal. But I might get confused if I, say, was looking at, say, y equals 3, and I was looking for an x-intercept, which says when y equals 0, what is x? But y can never be 0 because it's always 3. So I might get a little confused, but then maybe I remember, okay, this is probably just one of those special cases. There's no solution over here because I can never make y 0 because y is always just 3. Okay, so that wraps up the last little bit of 4.3. Again, we talked quite a bit about finding intercepts for the purpose of graphing and so on last time, but just a little bit of semantics on how do we report an intercept as an ordered pair, and what are a couple of these special cases. Okay, so we're the exam review. That's what we're going to do for the rest of today. So for the next a little over an hour, I have 14 questions. These are questions that are kind of similar to the types of questions you might see on the exam. And I think what I'm going to do is maybe take these in chunks of 2 or 3 questions. I'll give you an amount of time to kind of work through them. We'll come back together and then work on them as a class. We will go a little bit faster when I go through the answer today because this is a review. I want you to spend more of the time working on them and me less of the time kind of talking about them. So when I go over them, I'll go a little faster than I have in the past when we do this kind of worksheet type situation. But one thing that I'll expect from you is if I'm going too fast for a particular problem, or if you have a question or something, definitely stop me and ask to go over something a little more thoroughly, and I'm happy to do that. So I don't want to spend a lot of extra time going over something you guys already know and are comfortable with. But if I'm going too fast on a certain problem, or if you have questions on a certain problem, definitely stop me. I do want you to work through these, at your desk as you're kind of as we're going through these, and use them kind of as a self-assessment. So if you really struggled on a problem or a problem type, maybe that's something to review. And then, as I mentioned, I even made myself a little note down here for this one. I'll put it in bold so I don't forget to review these ones on WebAssign. So for these ones, we'll go through the math, but we'll also jump over to WebAssign and go through a couple of examples of the plotting tool just to review that one more time. Obviously, with the exam being through WebAssign, using that plotting tool will be important for the exam. All right, so let's start with these first 3 problems. It's 9 o'clock now, so let's take about 6 minutes to go through these 3 problems. These are kind of earlier problems. These might be a little more straightforward than some of the later ones. So we'll take about 6 minutes, work through these first 3 problems. We'll come back together, we'll review them, and take any questions, then we'll move on. And you can see, you get a sneak peek at problem 4 there if you were working ahead. So about 6 minutes, we'll come back together. Okay, it's about 6 minutes. So problem one, simplifying this expression. The real crux of this problem is making sure that this negative 1/3 that we have to distribute into the parentheses, making sure we're careful and distribute that negative as well. So negative 1/3 times 3 minus 1/3 times negative 9x. We multiply out, we simplify, we end up with 20x plus 41 after we cancel these two negative signs up here. Question 2 is m equals negative 3/4, a solution to the equation 7m plus 4 equals 3m minus 1. And the answer is no. And there's two ways we could have gone about this. One, we could just solve the equation. In this case, that might actually be the easier route, because if I strategize a little bit and look ahead and I say, wait, if I plug in m equals negative 3/4 into 7m and 3m, nothing's going to cancel nicely. I'm going to get a bunch of negatives. That might be a pain to work with. That's what I did over here. We could plug in, we could simplify everything down, and we could see that negative 5/4 is not equal to negative 13/4, so this is not a solution. But I think it would have actually been quicker just to directly solve and figure out what the answer is and ask, is the actual solution, is it negative 3/4 or not? In this case, we just move the 3m to the left side, move the plus 4 to the right side, and we end up with the actual solution is m equals negative 5/4, which is not negative 3/4. So no, negative 3/4 is not the solution. We know that for a linear equation like this, it's either going to have no solution, one solution, or infinitely many solutions. This is the case where we have one solution and it's not negative 3/4. And then for the third problem, we need to solve this equation. So the first thing we'll do is distribute on the left side to get 3x minus 12 plus 5 equals 17 minus x. Let me simplify. Minus 12 plus 5 is minus 7. Now I'll get my variable term on the left and constant on the right. I never know when OneNote is going to restart the numbering or not, but so add x to both sides, I'll add 7 to both sides, minus x plus x and minus 7 plus 7. I get 4x equals 24. I've isolated the variable term. I divide by 4 to isolate the variable. And I get x equals 6 as the solution. I can plug this back in. 6 minus 4 is 2. 2 times 3 is 6, plus 5 is 11. 17 minus 6 is 11. That looks good. Are there any questions on these first three? Okay, then let's move on to the next three. 4, 5, and 6. Sneak peek on 7 in case you're working ahead. But 4, 5, and 6. Let's take about 8 minutes to do these three. These are a little more involved than the last three, so let's take about 8 minutes, come back together, and work through the answers for these ones. And of course, as you're going along, if you have questions, if you come across a sticking point or something, you can always pop it in the chat. I'm watching the chat. And like usual, after a couple minutes, I'll kind of start working through the first problem. So that could also get you unstuck. But we'll take about 8 minutes for these next three questions, come back and talk about them. Okay, so these next three problems. For problem 4, we have an equation that has a bunch of fractions in it. So typically we want to clear the fractions first, especially in this case. None of these fractions really have denominators that work nicely together. So even if you like fractions, which very, very few people do like working with fractions, this is still going to be a pretty messy one to work with. So it would still be a good idea to clear fractions here, even if you weren't averse to working with fractions. We look at our denominators, 2, 3, and 5, and we find our least common denominator. 2, 3, and 5 are all prime numbers. So we can go through our process and we see the LCD is just going to be the product of the three numbers. The least common denominator is just going to be 30. We multiplied both sides by 30, just being very careful that we hit each term with a factor of 30. If we wanted to do an extra step and kind of do 30 times the whole left side equals 30 times the whole right side and distribute, we could do that as an extra step. That's no problem. We carefully go through and simplify all of our coefficients. 30 times 3 halves is 45, and so on. And we end up with 45x minus 10 equals 6x plus 15. That's a much nicer looking equation to solve. So we start by isolating the variable term, subtracting 6x over, adding 10x, and that gives us 39x equals 25. And then we isolate the variable dividing by 39. We get x equals 25 divided by 39. Is that in simplest form? 25 is 5 times 5. It's prime factorization. And 39, you can barely tell what I wrote there. But that is 39 is 3 times 13. So we see that 3 and 13 are prime numbers as well. There are no common factors, so this is the simplest form. That's our final answer, 25 over 39. For problem 5, we have a distributive property on the left and one on the right where we have to be very careful to distribute that negative properly. That negative 5 has to distribute to both the x and the 2. So we get 7x minus 7 minus 12x equals 3 minus 5x minus 10, making sure that negative comes along. On the left side, 7 minus 12, negative 5x minus 7 equals negative 5x. 3 minus 10 is minus 7. And we could either at this point see that we have simplified to negative 5x minus 7 equals negative 5x minus 7, the same thing equal to itself. Or we could go one more step and try to isolate the variable term by, say, adding 5x to both sides and adding 7 to both sides, and we get 0 equals 0. So first, all of our x's went away. All of our variable terms went away. And second, the resulting equation, 0 equals 0, is the correct equation. Is 0 equal to 0? Yes. This, therefore, is an identity. It's a statement that's always true. So all real numbers are solutions. Again, and thinking back a little more fundamentally, if I have the statement 0 equals 0, does picking x equals 3 or x equals negative 100 affect that statement at all? No, it doesn't. It doesn't matter what I pick for x. 0 equals 0 is always a true statement, but that statement is logically equivalent to the original statement, the original claim. So that original claim is always true no matter what I pick for x. If we had, let's just say, for instance, if we had gone through and we had, got something like negative 5x minus 72 equals negative 5x minus 7, what about this? Well, this is always false. This is a contradiction. I can see that because whatever number I put in for x, if I do negative 5 times that number, that's going to be a certain number. If I take that same starting point on the real line, on the number line, and on one hand I subtract 7, and on the other hand I subtract 72, In one case, I go to the left 7 units. In the other case, I go to the left 72 units. I'm clearly always going to end up at a different place, regardless of where I started with from my negative 5x term. Or in this case, what would the next step look like? So if I had, again, just as an example, if I had done my simplification and got negative 5x minus 72 equals negative 5x minus 7, if I add 5x to both sides to say get the variable term on the left, I end up with 0 equals, and then if I add 72 to both sides, on the right side, I end up with 72 minus 7, or 65. So now I'm saying no matter what I choose for x, the truth value of my statement is always just the truth value of 0 equals 65. This is always a false statement. Since 0 is never equal to 65, no matter what x I pick, the left side up here, again, hypothetically, if we had started with an equation that yielded this line here, then the truth value of the original equation for any x would be false. We would call that a contradiction, and we would say that it has no solutions. So those are our two special cases. The one we actually observed in this problem, the identity, where we get something like 0 equals 0, or left side equals right side, but all the x's go away. And all real numbers are solutions. We have infinitely many solutions there. Or the other option is, or the other special case is getting a contradiction, having all of our x's go away, but ending up with a claim that is false, ending up with an equation that is never true. That's like what we call a contradiction, and that has no solutions. So that would be the other possible special case. We didn't see that in this particular problem, but that's what it would look like. These last couple steps is what it would look like in maybe a different problem. And then lastly, solving an equation with decimals. We could note that the most number of decimal places we have is 2, and we can multiply by 100 to get rid of those. So we'd get, say, 125y minus 375 equals 250. But we might also notice that just multiplying by 4 does the trick, and that's a much smaller number to multiply by. So 4 times 1.25y minus 4 times 3.75 equals 4 times 2.5. And if we're multiplying decimals like this, one little trick that we can use is we can actually use the distributive property. So 3.75 is 3 plus 0.75. So I can make 4 times 3.75 equal to 4 times 3 plus 3/4, or that's 4 times 3 is 12, plus 4 times 3/4 is 3, or 15. And same thing on this first term. 4 times 1.25 is 4 times 1 plus 1/4. 4 times 1 plus 4 times 1/4. 4 plus 1 is 5. So when I do all of my calculations, I get 5y minus 15 equals 10. Isolate the variable term by adding 15 to both sides gives me 5y equals 25. Isolate the variable by dividing by 5, and I get y equals 5 as my solution here. Are there any questions on problems 4 through 6? Anything anybody want to see in more detail or anything?
So it's basically you try to find the lowest common factor for the denominators, then multiply by that.
Yeah, it's a very similar, in this case, it was a very similar idea to clearing fractions, in which I'm trying to find the smallest number I can multiply by and still get rid of the decimals. I just happen to notice here that 0.25, 0.75, and 0.5 are all quarters. 1/4, 2/4, and 3/4. So by multiplying by 4, I can reinterpret these decimals as fractions, and I see that by multiplying by 4, that will do the job. If you had multiplied by 100 instead, no big deal. You would just have bigger numbers at the end that you'd have to when you kind of isolated your variable, you might have a little bit extra simplification or canceling to do in the resulting fraction, but multiplying by 100 would still work here as well. Yep, either way would work.
Okay.
Yeah, but I was thinking of this more along the lines, like you said, of almost like finding a lowest common denominator. What's the smallest number I can multiply by that will do the job of getting rid of the decimals? Any other questions? Okay, so let's take a look at problems 7 and 8. Problem 7 is a fairly straightforward problem. Problem 8 might be a little bit more complex. So let's take about actually 6 minutes for these two problems and give problem 8 a solid shot and see if you can come up with a strategy for problem 8. Again, problem 8 is a more challenging problem, but I think it's a mixture problem that you might actually be interested in solving in real life, not like, one of these made up ones with coins or where somebody knows that, I forget how many people bought each of these two tickets, but I know that 10 more people bought this kind of ticket than like nobody ever knows that. Nobody ever has that set of information, but this might be a problem that a person might actually be interested in solving. So it's a little bit more challenging than the ones we've covered, but give it a crack. See if you can work your way through it. So about 6 minutes or so on these two. Okay, let's try to work through these two. So again, problem 8 is a pretty challenging one. It might be the hardest problem on this whole review. So if you didn't quite get it, don't feel bad. But I just wanted to show you that some of these things, even though in the textbook you look at some of these problems and think like, who would ever have this information, who would ever care about this? They do apply to some real world situations, but sometimes the real world situations, the numbers are just a little messier, or they're a little more complex than some of the made up ones. So some of these problems are kind of toy problems meant to give you kind of a stepping stone to maybe a real world problem later on. But okay, problem 7, a more straightforward one. Caesar's planning a 4-day trip to visit his friend at college in another state. It'll cost $189 for airfare, $51 for local transportation, $45 per day for food. He has $175 in savings, can earn $35 for each day or for each lawn he mows. How many lawns must he mow to have enough money? Does it matter that it's at a college in another state? I don't think so. The airfare, the local transportation, $45 per day. So it is important that it's a 4-day trip. So what is his cost going to be? It's going to be $189 for airfare, $51 for local transportation, and $45 per day. So 45 times 4 days for food. And what he has, basically his assets, his cash is 175 plus 35, let's say times L, where L is the number of lawns that he mows. If he has enough assets, enough cash to cover the cost, he is good. So let's figure out what is this cost. So we need to do 45 times 4. So 45 times 2 is 90, times 2 is 180. So we have 180 plus 9 plus 51 plus 180. 180 and 180 is 360. And then 51 plus 9 is 60. So that's $420 he needs. And the amount he'll have after mowing L number of lawns is 175 plus 35L. So we just set these two equal to one another. And if we wanted to, I suppose we could even turn this into an inequality problem and make this a bigger than or equal to, but we'll stick with the exact problem statement from the homework. I just now have a linear equation in one variable. I want to isolate the variable term, isolate the variable, and simplify. So I get the 35L equals 420 minus 175. Well, that's 320 minus 75. That would be 300 minus 55, or I think that's 245. And then L is 245 over 35. I know 35 times 2 is 70. I could chip away at this factor by factor, but let me see if it comes out to be a whole number. 35 times 2 is 70. 70 times 3 is 210. And then 210 plus another 35 is 245. So 35 times 2 times 3 is 210. 35 times 6 is 210 plus one more to get to 245 gives me 7. So that's how I would kind of approach a problem like this. Of course, you could, say, okay, I recognize that there's a factor of 5 in the top and bottom. Dividing a 5 out gives me a 7 on the bottom, and then whatever it gets you on the top. And then you could simplify again. You could do it that way as well. But Caesar has to cut at least 7 lawns to have enough money for the trip. Now, problem 8, again, a little more challenging of a problem. More challenging of a problem than you're going to see on the exam, but if you practice harder problems, then the exam problems seem simpler. So Bob is packing his lunch for today, consisting of grilled chicken and steamed white rice. Kind of a boring lunch, but only 2 things, so we only have 2 variables. He plans to eat 4 meals today and would like a total daily calorie intake of 2,200 calories and a total protein intake of 140 grams of protein. And he wants these spread evenly over the 4 meals. Maybe a pretty reasonable, amount of calories and protein for, for somebody who's like a moderate weight. Grilled chicken has 67 calories per ounce and 5.3 grams of protein per ounce. These are actual numbers for these items. Steamed white rice has 37 calories per ounce and 0.8 grams of protein per ounce. How many ounces of chicken and how many ounces of rice should he pack for his lunch so that he meets his calorie and protein intake goals? Okay, so let's figure out what we want to know. What is our end goal? How many ounces of chicken? How many ounces of rice? Let's call C the number of ounces of chicken and R the number of ounces of rice. I know also that I have some constraints. The goal is to achieve a certain number of calories and a certain amount of protein, certain number of grams of protein in this meal. So the total calories should be 2,200 over 4. Or I want 550 calories for this meal. And my grams of protein for this meal should be 140 over 4. OneNote just loves making my 4s into 9s. 140 over 4. The 140 over 2 is 70, and 70 over 2 is 35. So my goal for this lunch is to have 550 calories with 35 grams of protein. So on one hand, that's my goal. On the other hand, what's my actual number of calories given an amount of chicken and an amount of rice in ounces? Well, the calories would be, so chicken has 67 calories per ounce and rice has 37 calories per ounce. So mixing C ounces of chicken with R ounces of rice, I would have 67C plus 37R would be the actual number of calories in C ounces of chicken plus R ounces of rice. Similarly with protein, the chicken has 5.3 grams of protein per ounce. The rice has 0.8 grams of protein per ounce. So the actual amount of protein we would achieve with so many ounces of chicken and so many ounces of rice is 5.3 C plus 0.8 R. And we want to set these equal to one another. I have 2 equations and 2 unknowns. I know that I have a decent chance of being able to solve this with 2 equations and 2 unknowns. It's not like I have 2 constraints I want to satisfy with a single unknown. It's unlikely I'll be able to solve that. There's one thing that I would like to do first. I would like to take my second equation in protein and multiply it by 10 just to get rid of the decimals, make things a little bit easier on myself. Multiply through by 10 everywhere. 350 equals 53C plus 8R. Now at this point, it's important to note that at this point, this equation 350 equals 53C plus 8R no longer really directly ties. These numbers don't directly tie to our, actual, where we're not looking to get 350 grams of protein or anything like that. This is just saying, okay, the numbers in this box are the actual numbers that tie to my actual goals and calorie level and so on. But how can I make this a little easier to solve? I'd rather work with this equation than with the 5.3 and the 0.8. But it is important to note that since these are equivalent equations, when I get to the end and I get C equals number and R equals number, those will be accurate numbers for these ones. Okay, so what can I do? Now, again, this combination of two equations is a little harder than most of the equations we've seen so far. But we remember the general strategy. The general strategy was to solve one equation for one of the variables and substitute it into the other equation, and then multiply it and simplify. So let's solve this top equation for, let's say, C. So kind of an intermediate problem that we have to do to solve this overall problem is to solve this equation for the variable C. To do that, I subtract 37R isolating my variable term, and then I isolate my variable by dividing by 67. So this is actually another equation relating C and R that's directly related to my first equation up here. Let me clean this up a little bit. Now I want to take this and I want to plug it into my second equation, but not the one with the decimal points everywhere. I'd rather plug it into the one after I've gotten rid of the decimals. So now I have 350 equals 53 times C, but instead of C, I'll just put the stuff that's on the other side of this equation. Not the prettiest, but it is what it is. This is the downside of using actual real life numbers and actual real life scenarios, is that sometimes the numbers aren't as, pretty and nice as they are in the made up ones. I see now I have a single linear equation and one variable R that I'll be able to solve for R. At this point, I can completely forget for the moment about the application and just say, this is an equation in R. How do I solve it? I see a fraction. I can multiply through by the lowest common denominator, but of course, we only have one denominator, so I just multiply by 67 everywhere. On the left side, 67 times 350 equals 67 times 53 times numerator over denominator 67. The 67s cancel. And then 67 times 8R. So what do I end up with? I'm going to use my calculator for this. 67 times 350 on the left, 23,450. On the right hand side, I have a constant 53 times 550, 29,150. 53 times 37 is 1961. And 67 times 8 is 536. The steps that I'm doing aren't any different than the previous steps that we've done. The numbers are just a little more cumbersome to deal with. What do I do now? I simplify, I combine my like terms. So I have minus 1961 plus 536 is minus 1425 times R. Okay, now what do? I isolate my variable term. Again, no new math here. It's just the numbers are a little harder to work with, a little bigger numbers, but same strategy. 23450 minus 29150 is minus 5700. And then I isolate my variable. R is minus 5700 over minus 1425, or R equals plus. And if we do that division, we get 4. So at the end of all of this, R equals 4. We need 4 ounces of rice. Now we can come back up and we can use either equation or any of our previous equations. Let me go back to blue. Let's use equation 1 here for the calories. So we now have that 550 equals 67 times the number of ounces of chicken, which I don't know yet, plus 37 R, but R is 4. So I have 550 is 67C plus, and then 4 times 37 is 148. Solving this for C, I subtract 148 to get 67C equals 402. Or C equals 4 over 2 over 67, which is 6. So Bob should weigh out 6 ounces of chicken, 4 ounces of rice, and that'll get him the desired 550 calories with 35 grams of protein. I think the strategy was similar to a lot of the mixture problems we saw in chapter 3. It's just that the numbers were a little bit messier, right? We had bigger numbers to deal with. We had some fractions to deal with. We had some decimals to deal with. But this wasn't a whole lot different than, say, wanting to take a certain total amount of money and split it between 2 investments and get a certain interest rate, or mixing the other 2 solutions with different acidity levels, or 2 different combinations of items with different price points to get an overall total amount at a certain price point. It's the same strategy. It's just that the numbers were a little more cumbersome to deal with. But hopefully you can see that, this might be an actual problem that an actual real person might be interested in solving. If we wanted to go a little further and say, like, maybe we wanted a certain number of calories, a certain level of protein, and also a certain level of fat and a certain level of carbs or something, or we wanted to keep sodium below a certain level or whatever, we could build on the ideas of a problem like this. The problem would become more complex. We'd need different problem solving strategies to approach a problem like that. But this would lay the foundation for those kinds of problems. So as a general rule, if we wanted, let's say 4 criteria that we want to satisfy, say calories, protein, fat, and carbs, we would want to have um, four different contributions to our, four different food choices to mix together. There's also obviously the question of like, this is going to give a mathematical answer, but is that a reasonable answer? Like, if you had a little tiny bit of chicken and a ton of rice, like that's not something that most people are going to want to eat, just like a whole bunch of rice or a whole bunch of chicken and no, like very little rice or something. So there are also some practical considerations, but I think in this case, this turns out to be a pretty reasonable, like 6 ounces of chicken, 4 ounces of rice might be actually pretty reasonable. Throw some broccoli on there that basically doesn't really have any calories or protein, meaningfully to contribute. And, that wouldn't be, say, a bad lunch. So hopefully this convinces you that some of the stuff that we do in these applications isn't just to solve these goofy toy problems. It can actually be used in real life. Any questions on anything so far? And like I said, if you struggled with problem 8, this was definitely the hardest problem of, well, probably the hardest problem of the review and harder than the problems on the exam. So don't feel too bad about it. All right, so we have, I had 6 more problems on here, slated on here, but I'm going to skip these next 3 because we've only got 10 minutes left. And I'm going to jump right down to problems 12, 13, and 14. And I think we're going to focus on problems 12 and 13. So if you want to, you can, screenshot these or come back to the recording and work through problems 9 through 11, just as practice. You can work through problem 14 as practice, but let's take about 3 minutes. I think these should go quickly. Work through problems 12 and 13 in 3 minutes, and then we'll come back. We'll discuss the problems, and we'll go through an example on WebAssign. Okay. Sorry if my alarm startled you. I forgot I didn't mute myself that time because it was only a couple minutes. So problem 12, we see the y-intercept is a pretty nice number, 0, 2. If we try to find the x-intercept, it seems like that's going to be kind of a nasty number. It's going to be a fraction. But we can just pick a couple other choices for x, say x equals 1 or 2, get the corresponding y's, -1, -4. We plot our 3 points, and you could have used different points. You could have used -1 or -2 for x, or you could have used, say y equals 0, and what would that be? X equals, yeah, if y is 0, x is what? -2/3, I guess, or 2/3. So not the nicest number, but we pick 3 points, 2 points determine a line, and the third acts as a check. And that looks good. Problem 13, we have a line x equals 5. We're told it's a line, so that's implying that we're talking about a situation where we have two variables, say x and y. If I tried to find a point like 0, something, that's obviously not going to work because my x coordinate is not 5, and my equation on my line requires the x coordinate to be 5. Or 3, something is not going to work. But 5, whatever will work. 5, 1, 5, 0, 5, 2, they all satisfy the constraint that x has to be 5. So I could have a point like 5, 0, or 5, 1, or 5, 2, and I see that x equals 5 is just this vertical line. It's parallel to the y-axis that goes through the point 5, 0. Now let me switch up my share here. So I've pulled up a WebAssign problem. I got here by just bringing up an old homework and then clicking the practice another version button. That this is past due, so I can't actually continue working on the actual problem, but I can practice another version. And that gives me another one I can practice. So I'm going to graph x minus y equals 6 by plotting points. So over here, I want to graph x minus y equals 6. So if x equals 0, then I have negative y equals 6. Y has to be minus 6. If y is 0, I have just x equals 6. And if x is, let's say, maybe 2, then what do I have? 2 minus y equals 6. If I subtract 2 from both sides, negative y equals 4, or y equals -4. I use these 2 points to plot on my WebAssign graph, and then I'll use this one as a check to make sure that 2, -4 does look like it's on the line that's graphed. These should be easy numbers to plot based on this grid of integer points. So I go to my line here, click that. And again, I want to use my two-directional line. So it's a little strange when I click to make my menu come out, this first choice here is the line. So I click and I click in the same spot, and that selects the line. If I clicked and moved over to here or something, that would be the line segment or the unidirectional ray. But I want to just click and then click that same spot to choose the line. When x is 0, y is -6, so this is 1 point here. And then when x is 6, y is 0. Let's just say that I, plotted a point here. So there's my point. That's not the correct point, but let's say that I plotted this and I check, does this line go through 2 comma -4? X equals 2, y equals -4. No, it really kind of misses that. Something seems to have gone wrong. So I might want to, I can either click and drag my point to adjust my line. Now it goes through 2, -4. Or I could come over here to this graph layers. And I see, okay, what went wrong? I have 0, -6. That's the one point that I want. Oh, I want 6, 0. Maybe just my clicking was a little inaccurate. I can manually just enter 6, 0. And I see there's my line. And again, I check, does it go through 2 comma -4? Yes, it does. That looks good. And I can submit it for a grade. And I see I got it correct. I don't want to plot a whole bunch of extraneous stuff on here. I don't want to, 2 or 3 lines or other chunks of line segments or something. That's probably going to make WebAssign mark it wrong. I probably also don't want to plot a whole bunch of points. I think WebAssign usually, if you plot extra points and they are actually on the line, like say 2, -4 here, I think WebAssign is still okay with that usually. Yeah, it looks like it's still happy with that. But the more extraneous stuff that you plot on the plot, the more likely it is that you're going to make an error. So I would recommend just keeping it to just the line that you want to plot, and then having a third point that you kind of check. And I wouldn't even plot the third point, just because if you do plot and it's a little off, that's just one more thing that can go wrong. And then if I was unhappy with this, I could clear all. I could delete a particular component, or I could clear all to clear the whole graph. So hopefully that little crash course gives you a little more insight into how to use that tool. And again, there's the supplement on Blackboard, and we also went through this last class, so you can refer back to last class where I went into a little more depth and went through a few different problems.